So how do we change the basis of a field? So let's say we have a field f, which is a function of xy. And this is a vector field now, okay? And therefore, the value of this vector field is a vector, and therefore it has different components. For example, it will be f of x times x hat plus f of y times y hat, okay? Where each of these are actually a function of x and y. I didn't write it, but I could have written f of x as a function of x and y, and the same for fy, yeah? So this is written in rectangular basis. So what if we want to change this to polar basis? So what is our aim? Our aim is to write this same field in polar basis. So we want f rho times e rho hat plus f phi times e phi hat. Okay? So remember what that meant. I had an example here. So I have a vector, and I can either write it as 2x hat plus 1y hat using the x hat y hat basis, or this same vector, I can write it using e rho hat and e phi hat. Yeah? So how do we find these two numbers? How do we find those two numbers? Or actually, they will be functions in general, because this vector depends on position. So at different position, the vector will change. Therefore, these numbers will actually depend on position. They will be functions of position. And we want to change them into some other functions. Okay? So that's what we could write here as f rho and f phi, where now f rho is also a function of position, and f phi is a function of position. So how do we find these two functions if we know these two functions? Well, we need to change the basis, okay? And for that, you have studied linear algebra, so that's exactly how we can do it. There are actually different ways. So let me write the different ways. So we could choose to do projections with the inner product. So the first thing to notice is that always the unit vectors in polar, but also in spherical and in cylindrical, they are an orthonormal set. So the angle between them is 90 degrees, and they always have a length of 1. Okay? So they are orthonormal. And therefore we can apply simple recipes to find the components. So f is equal to the projection of f into the direction e rho, which is f inner product with e rho hat times e rho hat, plus the projection of f into e phi, which is f inner product with e phi hat times e phi hat. Okay, so these will be our new functions, f rho of xy and f phi of xy. So this is how we can find these two functions, by doing an inner product with the corresponding unit vectors. And remember, the unit vectors are given in the list of useful equations always. Yeah. So you have the unit vectors here for polar coordinates. Okay. What other method do we know to change the basis of a vector? We can use a change of basis matrix. How did the change of basis matrix work? We created this matrix, which we call the change of basis matrix, which is written as the unit vectors of the new basis that we want. So, for example, e rho and e phi, we write them as the two columns, and we write them in xy basis. Yeah. So we write if e rho in x hat y hat basis. Okay, as a column of two numbers, and the same for e phi. And this is the change of basis matrix. And then we know that the vector written in the polar basis, so the two components f rho and f phi is equal to the inverse of this matrix times the vector written in the x and y basis. So fx and fy. Okay, so calculating the inverse of this simple matrix, we can convert the functions fx and fy, which are the two functions here, we can convert them into the two functions f rho and f phi. Okay? Now, as an example for polar coordinates, what would this matrix be? This matrix would be equal to E rho hat written in rectangular in x hat, y hat basis. So E rho hat is cosine phi times x hat plus sine phi times y hat. So that's what we need to write in the first column. Cosine phi, sine phi. And in the second column, we need to write E phi hat written in x hat, y hat basis. So this is E phi hat written in x hat, y hat basis. So the first component is minus sine phi, and the second is cosine phi. So therefore, this is minus sine phi, and this is the cosine of phi. So that will be matrix A, and we can now calculate the inverse of this matrix, and therefore we can convert the functions fx, fy into f rho and f phi. Okay? The answer of you doing this method or doing this method will be identical. So it depends on if you are more comfortable doing inner products or doing change of basis matrix. And finally, there is often another way of doing it, which is by simple inspection. You might identify the unit vectors. So for example, imagine that your vector field f is given by cosine phi x hat plus sine phi y hat. Okay, so that this is your fx and this is your fy. So how do you convert this to polar basis? So actually quite often, with some intuition, you look at this and you say, wait a second, cosine phi x hat plus sine phi y hat, that is suspiciously similar to E rho hat. It's actually equal to E rho hat. Therefore, you can directly write that this is equal to E rho hat, which means that this is equal to 1 times E rho hat plus 0 times E rho phi. Sorry, times E phi hat. Yeah. So therefore, you have already found the two f rho and f phi. So just by inspection, you found that one of the unit vectors was included in your field, so you can just substitute it, okay? And there would be no need to write all of this. We don't have to write that. You just write E rho hat, and that's it, yeah? Okay, now notice something. Here I told you that f of x is a function of x and y, yeah? But in this example here, I gave you f of x, and it is not a function of x and y, it's a function of phi. So that's in general true. So f of x can be a function of x and y, or it could be a function of rho and phi. And the same with fy. And actually the same with f rho. So f rho could be written as a function of rho and phi. And the same with f phi. Which means that we actually have 4 possibilities. So this corresponds to changing the coordinates from rectangular to polar. And that's what we saw in the last video, how to change the coordinates, which was done by simply substituting. Yeah? So we can always change the coordinates. And the other thing is changing the basis, yeah, which means changing from fx, fy to f rho, f phi. But we can do one thing, or we can do the other, or we can do both, right? So actually I came up with this nice table, and I'm quite happy with coming up with this because I don't usually have found this in any book. It just was, I thought it would clarify things. So a vector field, f of r, and notice that this is bold, which means that they are vectors. Yeah. So this is a vector field. So you can write it in 4 different ways, and that's why I have 4 spaces here. So on one side, you can change the coordinates, which are the input. And on the other side, you can change the basis, which is how do you write the vector f? In which basis do you expand this vector? Yeah. So the coordinates can be written in rectangular coordinates, which are x and y, or they can be written in polar coordinates, which are rho and phi. While the basis, you can choose rectangular bases, which are x hat and y hat, or you can choose polar bases, which are e rho hat and e phi hat. Okay, so in total there are 4 combinations, 4 different ways in which you can express the same vector field in 2 dimensions. In 3 dimensions, it's even worse because you have rectangular, cylindrical, or spherical. So the coordinates can be one of the 3 options, but also the basis can be one of the 3 options. So in total, you have 9 different possibilities, ways of expressing the same vector field in 3 dimensions. Okay? So very often, one of these 4 is much simpler than the other 3, and that's the one people would choose to express that vector field. Okay? So for example, the gravitational field, I bet when you have seen the gravitational field written, so the gravitational field is minus g m over r squared er hat. Okay, so this was chosen as, what are the coordinates of this field? So the coordinates are the things that are not a vector, so it's r. This is the spherical radial coordinate, the distance to the origin, right? So this is written in spherical coordinates. And in which basis is this field written in? Well, it's written in the er hat, so this is spherical basis. That's because the gravitational field has spherical symmetry around the mass. And therefore it makes sense to use spherical coordinates and also spherical basis, okay? If you tried to write this same vector in Cartesian coordinates and in Cartesian basis, you would start having horrible square roots of x squared plus y squared, yeah, things like that. Not to mention er hat written as a function of x hat and y hat. It would depend on where you are, so it becomes an ugly mess. While writing it in spherical coordinates and spherical basis is very simple. So there are many problems in the notes of filling up this table for different initial functions f of r. I recommend you go through them and make sure you understand all of them, but we will do one example.